So hi guys, so welcome to another dose of integration. We've just finished antiderivatives and now we're going to look at something called the definite integral. So pause the video, go back to the previous video on antiderivatives and the indefinite integral. Make sure you understand what's going on there, and then all we're going to do is just put in some numbers and give this thing called the integral some sort of, I want to say, physical interpretation, but some sort of interpretation, something that we can relate to in everyday life. Like, for instance, the area under a curve. What would that mean in terms of the integral? So just go back to the previous video, spend a few minutes there, and come back to this amazing lecture. Okay, so if you look at this, what we call the definite integral, you see immediately there's a difference between what we've just finished in the previous lesson, and that is with the indefinite integral there were no numbers, let's put it that way. Over there it was just a plain simple long S-type integral sign, but suddenly we have what we call the bounds. So A, B are the bounds, and the way we read this, I'm looking at the left hand side here, it is the integral from a to b of f of x dx. The integral from a to b of f of x dx. Okay, so firstly, let's forget about the bounds. Remember what we said about the integral? Integral of f of x dx, we are looking for a function whose derivative is little f of x. Now we're putting the bounds. So we're evaluating, firstly, if you look at the right-hand side, that antiderivative at the top bound. This is the top bound, and this is the bottom bound, minus f. Okay, so before we sort of churn out these integrals, I thought maybe it'd be best if you saw some pictures. It's always nice to learn from pictures. So I've got three different graphs, and I'm looking at the area under each one, and that is the blue shaded region. So if you look at the first one, the extreme left, you have a rectangle, and if I asked you what is the area of this blue region, I'm shading it red. You see it's a rectangle, so the area would be nothing more than the length times the breadth, and so it's 1 to 4, so that's 3 units. So the length would be 4 minus 1. You have to be very careful. It's not starting at the origin, you see. And the height of that thing is 2 minus 0, which is that distance over there. So 4 minus 1 is 3. 3 times 2 is 6. Arbitrary units. If you're assuming that the length and the breadth were in meters, then your answer would be in meters squared. You agree with me? How about the next one? If you look at the next one, that's interesting. How would you work out the area of that shaded region, the blue region? So a lot of you say, well, I can see a triangle and a rectangle. Okay, let's go with that. Triangle plus rectangle. So there's the rectangle over there. And what's the length of the rectangle? Watch this. So it's length times breadth for the rectangle plus half base times the height for that triangle. Agreed. The length of this rectangle is 2 minus 1, which is 3. The height of that is going to be 1. The base would be the same, so it's 3. And the height, be very careful here, of that rectangle, it's 4 minus 1, which is 3. So that's 3 plus 9 over 2, is that right? And that becomes 15 over 2, let's say meters squared for now. So is there another way of actually working this out, geometrically, if we can work this out? Now this reminds me of a trapezium. If you look at that shaded region, it's a trapezium with two parallel sides. How would you work out the area of a trapezium? Recall from school, the area of a trapezium is half the sum of the parallel sides times the perpendicular distance between the side. So let's see whether we can get this. Is cool. The first side is 1, the height is 1. The next side is 4, so that's 4. And the perpendicular distance is 3. 2 minus 1 is 3. Let's see, 4 and 1 is 5. 15. 15 over 2 meters squared. So it's so important that you don't forget those basic shapes, the polygons, the quadrilaterals that you studied way back then. All comes back into play right now. So it's very, very important that you don't learn in little compartments, where you forget things and you move on to new things. Just carry that knowledge forward, and that'll be very, very useful to you. How about that last one? What's really happening in that last one, if you look at the quarter circle over there, what's really happening in that quarter circle? Well, the quarter circle, we know that the area of the full circle is pi r squared. So the area of the quarter circle will obviously be pi r squared divided by 4. But you look at the radius of the circle, that should be a straight line, is 1. So it's 1 squared over 4. And so that'll give you pi over 4 meters squared. And there we have it. Pretty awesome, right? Cool stuff, man. Okay, so let's try to get a sense of this definite integral, and I want to look at it as, or interpret the definite integral as an area under the curve. Now I've got to point out that this is just an entry interpretation. Most people, if you look at calculus textbook, they speak of calculating the area under the curve, but the area under the curve could actually have another meaning. It's not just like painting a wall. How much of paint do I need? And I work out the area. If you look at, for instance, mechanics, you look at the force versus time graph. What does that give you? The area under the graph. F delta t gives you the impulse. Okay, but for now we're going to keep things very, very simple. We're looking at the area under the curve. And for this graph, you can see that the y-intercept is 2, the x-intercept is minus 2. So this curve must have equation y equal mx plus c, y equal to x plus 2. That's the first thing you want to verify. The next thing I want to do is work out the area from minus 2 to 4 under this straight line. So firstly, I want to do this geometrically using some very simple math we learned way back in grade 8 or something like that. And so what we do is say, okay, the area under this curve is the area of the rectangle. It's base times the height divided by 2. The base, be very careful, it's 4 minus 2 is 6. The height of this guy is 6. So 36 divided by 2, and that gives me 18 meters squared. Okay, so it's pretty straightforward. Now, the definite integral, let's try to bring that in there. So if I want to work out the area, let's go, area is the integral, but from minus 2 to 4, that's where the x runs. And the equation, the function f of x, is x plus 2 dx. Let's integrate that. What is the integral of x? That's x squared over 2 plus. What's the integral of 2? It's 2x. And that integral is evaluated from minus 2 to 2. Oh, sorry, 4. So the first part, if you don't worry about the bounds, it's a normal definite integral. X plus 2 we can all integrate, and that is x squared over 2 plus 2x. But now we've got minus 2 to 4. So that's going to give me... Now watch how I evaluate this thing. You got to evaluate the top bound first. So you take the antiderivative, if you're going to call it, and evaluate it at 4. So that's 4 squared. I'm going to write it like this. Plus 2 into 4. And then it's minus the bottom bound, watch that, which is minus 2 squared over 2 plus 2 into minus 2. Right, so that's 4 squared over 2, that's 16 over 2, that should give me 8. 2 times, that is going to give me 8 minus into, look at this, minus 2 squared is 4, 4 over 2 is 2, and then minus 2 times 2 is minus 4. And look at that, for sure as God made little apples, what is that equal to? Think about that. It's equal to 18. 8 and 8, 16 minus 2 gives you 18 square meters. Is this coincidence? No. So the definite integral, in a very crude way, let's put it that way, I've shown you, is equal to the area under that curve. Of course, we are also assuming the curve is always going to be well behaved, smooth, continuous, and so that we can deal with these. And of course, why do I use the word of course so many times here, or that phrase? Yeah, we're going to make that assumption, but later on you're going to be looking at jumps and discontinuities, and that's when you go to university, things become really exciting. Okay, so the previous question we dealt with a straight line, and you could have used a geometric approach and worked out the area under that curve or the straight line. What about working out the area trapped between that blue curve and say the x-axis, where x runs from -4 to 2? So we know from our discussion that the area is nothing more than the integral from -4, watch how I read this, from -4 to 2, and the function itself, if you read there, is minus x squared minus 2x plus 8 dx, which is the inverted parabola. And no prizes for guessing here. What is the integral of that? That's just a polynomial, so it's minus x cubed over 3. We're adding 1 to that. Integral of x is x squared over 2, and then this 8x from -4 to 2. Always check, if I differentiate that, I must get what we call the integrand. Okay, now we must evaluate at the top bound first. So that's -2 cubed over 3. This guy will cancel, so I'm just writing this out slowly so you can see where the constants go in, and then remember it's the minus sign bracket now at the bottom bound. Lots of minus signs there. And then you've got a minus, and then it's squared plus 8 into -4. Now you could quickly use your calculator and you can simplify this. Let's see whether we can. That's -2 cubed. Sorry, that's 2 cubed is 8, so that's -8 over 3. That's, well, lots of minus signs popping up here. You have to be very careful. This minus, the use of the brackets is so important. I can't emphasize that more. -4 cubed is -64, but there's a minus sign out there. Oh my goodness. 64 over 3 minus that squared, so that becomes -16, and then -32. So then becomes minus, you're going to simplify the 16 minus 4, that's going to give me 12 minus, you got 64 over 3, and then you got -48. Now watch, you see that minus sign, and the minus makes it positive. So I'm going to get something like 12 minus -48, so that gives me 60. Please check my work. -72 over 3. Something like that, yeah? So 60 minus 72 over 3, whatever the units are, and that gives you the area between that blue curve and the x-axis. It's pretty straightforward. It's just now finding the antiderivatives, evaluating at the bounds, and boom, you got your answer. Very powerful. Okay, so they can also ask you to work out the area between curves. Between curves. So if you look here, I've got two curves, y equal to f of x, which is the blue curve, and I've got y equal to g of x, which is the red curve. And I want to find the area of that green region. So the bounds are from A to B. And you can see very quickly, if I want the area, remember, I want to sum this up as a series of rectangles. So if I basically partition, that's the word. And we did this earlier on, right? So please go back to that, into a series of rectangles, and then sum up these rectangles, the areas of these. In that particular limit, I should get the area of the green region. So we can write the area between these two curves from A to B. It's the top function minus the bottom function dx. There you have it. So maybe in general, so a is equal to integral from a to b f top minus f bottom dx. And that is exactly what we want you to do in tests and exams, not just for your school, but for university as well. Very, very powerful method, this one. Okay, so here's a typical test question. I don't keep like saying test question. Are we doing mathematics just to write tests and exams? Are we doing mathematics for life? You know, if you do mathematics for life, you'll always remember things, you'll always do well, and you'll excel. But if you keep learning to a test, then your knowledge is very focused, it's very limited. Okay, so change the way you learn. You can change the way you think. And if you change the way you think, you can change the world around you. Powerful stuff, guys. So what is the area bounded by the curves y equal to x squared minus 1, which is the parabola, which is the blue curve? And then you got the straight line y equal to 2x plus 7. That's the first thing you need to realize, okay? Which is the blue curve, which is the red curve. Now, if you think about this, we're going to work out the area, we're going to partition in vertical strips. So if we want to do that, if you're going vertical strips, then the area is from whatever a to b. I like to write as f top minus f bottom dx. Okay. Now the first thing we need to find out, and this is where you start getting marks and earning marks, is a to b. What is a? What is b? Well, you can see that it's the point of intersection of these two graphs. So in order to find AB, work out the intersection of those two graphs. So we're going to say x squared minus 1 must equal to 2x plus 7. Agreed, that's where the graphs intersect. So we got x squared, bring that becomes minus 2x, 7 becomes minus 8 equal to 0. And what are the factors of 8 that'll give you? And this is a nice way of actually checking your factorization. 8 would be 1 and 8, 4 and 2. 4 and 2 is nice, and the 4 must have a minus sign, the 2 must have a plus sign to get a minus 2 in the middle. Double check that. So it tells us straight away x is 4 or x is minus 2. So this obviously is minus 2, and this is. Okay, so continuing from the previous slide, we remember we had x equal to minus 2 there, and if you remember, that was x equal to 4. So that's our bounds on the integral, and now we want to work out the area. Now that's pretty straightforward. We can see immediately the top function is the straight line. So let me just go a, b, general formula, top minus bottom. We integrate with respect to x. So it runs from minus 2 to 4. The top function is 2x plus 7. The bottom function is x squared minus 1. Watch the brackets. Beautiful, beautiful. Okay. And just simplify the inside and integrate. So we still got 2x plus 7 minus x squared plus 1 dx. Little more simplification, you don't really have to. I'll bring the minus x squared there as a leading term. Then the 2x is there, and 7 and 1 is 8 dx. And now start integrating. So the integral of minus x squared is minus x cubed over 3. Integral of that is nothing more than 2x squared over 2, and that is 8x all over. Does this look familiar? Well, look at the previous problem and you get exactly the same thing. So please evaluate this integral and check it with my previous answer and see whether you get the same. So it's very important that you understand how we substitute top bound first minus then the bottom bound to get your final answer. So please complete that for me and make sure you understand what you're doing. Okay, so what have we here? We have a straight line intersecting a parabola. They were kind enough to us. They gave us the points of intersection. So it's minus 2, 4, 3, 9. So x is minus 2. And the other point of intersection is x equal to 3 there. Y value being 9. And you want the region of the blue region of the blue area. The area of the blue region. Gosh, man. So let's have a look. So the area, see, we're going to partition like this. Now we're going to cut them into vertical strips. So if it's vertical, the area would always be from A to B. It would be F top minus F bottom dx in this case, because it's x here. And we know it runs from minus 2, that's the point of its intersection, minus 2, and it runs all the way to 3. The top function, which is the straight line, is x plus 6. And the bottom function is the parabola y equal to x squared. It's nice, simple, compact problem. Minus 2, 3. So that is minus x squared. I'll give this the leading term plus x. You don't have to change the order, but I like doing that. Dx. Integral of minus x squared is minus x cubed over 3. Integral of x, nicely done, is x squared over 2. Integral of 6 is 6x from minus 2 to 3. And now evaluate at the top bound. So minus into 3 cubed. It's nice to put them in brackets. Plus 3 squared over 2. Write neatly. This is terrible writing. Minus, watch this big fat bracket over there like this. And then you evaluate the bottom. Now here you have to be very careful. Lots of minus signs. Minus into minus 2 cubed plus minus 2 squared over 2 plus 6 into minus 2. And that's pretty straightforward. That is 27 over 3. That gives you a minus 9. That's 9 over 2, and that's 18. So you can actually start evaluating this. Let me just give you one step, and then it's pretty straightforward after that. So this term is 27 over 3 with a minus sign becomes minus 9. This is 3 squared over 9. 3 squared is 9, and 9 over 2. 6 times 3 is 18. That's the first bracket, the whole thing done there. Not the first 3 terms. And you've got minus into 2 cubed. It's minus 2 cubed is minus 8, and minus becomes 8 over 3. Lovely, beautiful. And then you've got minus 2 squared. Minus 2 squared. Minus 2 squared is going to be plus 4 over 2 is 2. And the last one is 6 times minus 2 is minus 12. And here's my challenge to you. Simplify that stuff, and that'll give you the area of the blue region. Pretty straightforward, guys. Come on, do some work. Oh, what does this look? It's like a genie coming out of a bottle there. So you got 2 curves, and it's interesting here. Because if you try to cut vertically, you're not going to go anywhere, right? Think about that carefully. So it tells you if I want to work out the area of the green region, what if I cut this area or partition this area with horizontal strips? And if you look at horizontal strips, then each strip has a width dy. See, so we integrate with respect to y. So your function, instead of writing in terms of x, must be a function of y. And then the area now is whatever the bounds are, wherever the bounds are. Let's say A to B, but in this case it's from C to D. Y runs from C to D, so just to distinguish. And it's the left function minus the right function. You see, that will be the length of the rectangle. Left minus right. So it'll be right. I'm thinking of the other right hand. F right, which is the blue curve, minus F left dy. So in this case, it's the integral from C to D. I'm just going to use the notation here. It's f of y minus g of y dy. And that's how you work out the area if you are now partitioning horizontally. And for some curves, this is very, very important, as is the case with the next example. What I'm going to do here is to have a look at these 2 curves. So you have a curve x equal to y squared, or y equal to root x, and then you've got y equal to x minus 2, which is this purple line, the straight line, and they want you to work out the area of that shaded region. Now, let's assume that we're going to blindly go in there and partition vertically. So if you look at vertically, you see, so it'll be top minus bottom, top minus bottom, top minus bottom, top minus. It's the same thing, but now you see when you hit this point here, the point of intersection, it's top minus bottom of the blue curve. Now suddenly, from the point of intersection to that point, let's take an example from here. Look at that. You see, so the top is still the blue curve, but the bottom is now the purple curve. So basically what it tells me that if I want to integrate this thing and find out the area, I've got to split this blue region into two parts. So the area would be the sum of A1 plus A2, where A1, the area, let me write it like this, A1, it runs from 0 to the point of intersection, which turns out to be 1, plus the area A2, which runs from the point of section 1 to 4. So this area can be done, and I'll actually do that in the last slide of this lecture to show you that you can split the area up if you want to stick to vertical partitions, or you can just do it in one go using horizontal partitions, which is what's going to be done in the next slide. So the choice has to be made. The choice has to be a clever one. It doesn't have to even be an intelligent one. So okay guys, so the same problem, right? So we got those two curves, the parabola, and we have the straight line, and we want to work out the area of the region. But what I want to do is tackle this question using a horizontal strip as opposed to a vertical strip. So if I just drew typically a rectangle of that order there, then you'd find that not the height but the length of the rectangle is nothing more than it's the purple line minus the blue line. So we want to use that general formula in this case, say from C to D, and it'll be the function on the right. Does that look like fright? Weird. Minus function on the left, not dx but dy. So we need to write this as a function of y, which we've already done there, and next is y plus 2. So it's it's a right function minus the left function, and in this case the y values, the lowest y value is minus 1 and the upper y value is 2, so it'll run from minus 1 to 2. The left function is y plus 2, you see that, minus the right function is y plus 2. I'm getting my hands mixed up here. Minus y squared, big bracket on the outside, dy. Integrate this. So y plus 2 minus y squared, I'll write it as minus y cubed over 3. Integral of y is y squared over 2. That's a 2, by the way. And the integral of 2 is 2y, running from minus 1 to 2. Simply just equate. So you get minus, you're going to get 2 cubed over 3 plus 2 squared over 2 plus 2 into 2. And then remember our famous minus sign. And let's be careful here now. Minus 1. I don't know why there's so many minus signs in these things. And then you simplify that. Yeah, don't use your calculators. These things are easy. Like 2 cubed is 8, so it's minus 8 over 3. 2 squared is 4. 4 over 2 is 2 plus 4. And then you got a minus 1 cubed. Be careful. Minus sign, minus plus. So it's 1 over 3. Minus 1 squared is plus 1 is a half. Minus 2 with the big fat minus sign in front. So basically what you do is you simplify the brackets, knock in the minus sign, and then add to the other 3 terms. You'll have the area. Beautifully done. So let's do it. Let's see whether we can actually get the answer out. I'll tell you why in a short while. So minus 2 cubed becomes minus 8 over 3, which is that term. 2 squared over 2, that becomes 4 over 2, which is 2. This is 2 times 2, which is 4. We've taken care of that. Minus into. Minus 1 cubed is minus 1 plus, that becomes plus 1 over 3. And it's minus 1 squared, that becomes a half. Nasty, nasty, nasty. 2 times minus 1 is minus 2. And so there we have it. So we have like something like 6 minus 8 over 3, which is 18. 18 minus 8 over 3 is 10 over 3. Just going to squeeze that through there. Beautiful, right neatly. So these three terms, see 4 and 2 is 6. It's common denominator 3 is 18 minus 8 over 3 is 10 over 3. And then we got a 6. So 3 goes into 6 2 times, 2 goes into 6 3 times. So that's 5 over 6 minus 12 over 6. 5 over 6 minus 12 is minus 7 over 6. Minus 7 over 6, and a minus sign becomes plus 7 over 6. It's how beautiful it is to do mental math. So 3 goes 6 2 times, that's 20, so it's 27 over 6. That's your final answer. The final answer I'm getting is 27 over 6. Whatever the units are, meters squared or whatever they. Please check whether you agree with me. 27 over 6. I'm just doing this mentally. You are pressing those calculator buttons. No, don't do that. Keep your mind alive, fresh, young, filled with curiosity. Okay, so what I'm going to do now is to split this up. I want to use a vertical strip and show you that it still works. A little bit more painful though, and these are simple functions, so we don't have a problem with that. So I'm going to integrate this in terms of two areas. The total areas will be A1 plus A2. And so A1 is this red region over here, and whatever is remaining, the sum of those two will give you the total area, which is the area of the blue region. So for area A1, watch, it runs from 0 and x is 1. And it's the top function minus the bottom function, but you've got to be careful. The top function minus the bottom function. On the top, y is equal to root x. At the bottom, y is equal to minus root x. Be very careful. So root x minus root x, big bracket there, dx. So that takes care of the red region that I just shaded. Now what about the other one? Well, there x runs from 1 and it runs all the way to 4, and the top function is still, in this case, root x, but the bottom function is a straight line, which is x minus 2. Watch how beautifully I write the dx. So what is root x minus root x? So 0 to 1, it becomes 2 root x dx. Simplify from 1 to 4. So this becomes root x minus x plus 2 dx. The 2 is common, so write this as, not common, but it's a constant. You can take it out. Root x, remember we always wrote it as x to the power half plus integral from 1 to 4. This would be x to the power half minus x plus 2. Watch the brackets, watch the brackets. And now we integrate. Do you recall what's the integral of x to the power half? Well, x to the power half, there's that 2 there. X to the power half would be x to the power 3 over 2, and then it's 2 over 3 here from 0 to 1. You remember that? Yes, very good. And then you go again, 2/3 x to the power 3 over 2 minus x squared over 2 plus 2x, but this runs from 1 to 4. And you can see typically here, if I evaluate this, this is just going to give me the first bracket over here. It's going to be 4 over 3. All right, and the next bracket here, obviously, 4 to the power 3 over 2 is what? Well, 4 is 2 squared, so that becomes 2 cubed is 8, 16 over 3. So let me just quickly squeeze this in here. There's a 1, so 1 to the power 3 over 2 is 1, 2/3, so this becomes 4 over 3. The 0 does not count. Plus, watch this. You're going to follow me. Put 4 in there. 4 to the power 3 over 2 is 2 squared. So that becomes 2 cubed is 8. So that becomes 16 over 3. Beautifully. All in the mind. 4 squared is 16. So minus 16 over 8 is minus 8. And 2 times 4 is 8. The 8 and minus 8 will cancel. Now to evaluate at the bottom bound, you're going to put a bracket in there. 1 times minus 2/3. That's a minus a half plus 2. So I'm claiming, okay, so you got minus 2/3 plus a half minus 2. You simplify them with the calculator, you'll get exactly exactly the same answer I had in the previous slide. If you don't, give me a call or send me an email. Cool stuff, guys. It's a beautiful section. Very, very important for test exams and life itself in general. So, make sure you understand it before you move on to the next section.